Okay, hi everyone. We're just gonna wait on a few more people to join and then get started. Our instructors are also running a bit late today, so I'll just get you guys started. So yeah, hopefully everyone can see me in my screen. Um, Let me know if there's any problems. Okay, yeah, so yeah, I'll just let a few more people in, then we can get started. Okay, I think we're fine to make a start then. Hopefully everyone has received the handout as well. Let me know if there are any problems. But yeah, let's just make some. Cool. Okay, so today is the second session of algebra, and the topic for today is inequalities. Is the share screen working? I feel like it's not. Hold on. Hey guys, can you let me know in chat if you're able to see? Oh, okay, cool. Can you guys see this next slide with like the table of contents? It says it's loading. Yeah, I think there's like problems with, wait, hold on, maybe. Yeah, there's some problem with full screen, so I'm not really sure. Okay, that's fine. Let's just not use full screen for now because I think it isn't working too well. Okay, so today we'll be going over two kinds of inequalities. The first is the AMGM inequality, and the second is the Cauchy-Schwarz inequality. So firstly, let's talk about what inequalities actually are. Okay, so this slide is pretty text heavy, but ultimately, I think what inequalities focus on are they focus on optimization, usually by determining maximums and minimums. So they often involve algebraic expressions, functions, and operations, but they often go beyond simple relationships, simple equations to explore the relationships between different quantities. And in Maths Olympiad, you'll often encounter a variety of problems that require creative thinking, strategic approaches, and pretty deep understandings of mathematical concepts that can go from basic inequalities, where examples can seem almost a little obvious, to more complicated mathematical structures. Oh, is our instructor here? Perfect. Alan, you can take over now.
Okay, hi guys, I'm sorry I'm so late. Let me quickly get the screen share ready.
Yeah, that's all good. That's all good. Just let me know if everything's working, and then make you host. Okay.
Sounds good.
And by the way, I just got up to like introducing what inequalities are. So yeah. Can you record as well?
Is the screen share working?
Yeah, it's working. Can you like record the meeting as well? To yeah, and just check that it works. Because I'm gonna
I think the meeting's still recording.
Oh wait, okay, let me just stop that. Wait, I'm just gonna leave and then I think you can do it.
Okay, so what are Olympiad inequalities? Olympiad inequalities are a branch of Olympiad algebra that basically focuses on finding the relationship between two expressions through algebraic manipulation and maxima and minima. That's basically what this is. And then, wait, I'll just let some people into the meeting. So now we will cover an overview of basic inequality notation. We say A and then larger than B if A is greater than B, or A minus B is larger than 0. And A smaller than B if A is smaller than B, or A minus B is negative. And we say that A is larger than or equal to B if A is greater than B or can be equal to B. And A minus B is non-negative, so it can equal 0, but cannot be negative. And then we also say A is less than or equal to B if A minus B is non-positive or cannot be positive, but it can be negative and can be 0. And then if A is larger than B, then B is smaller than A, and vice versa. Some properties are if A is larger than B, then A plus C is larger than B if C is non-negative. And if A is larger than or equal to B, then A plus C is larger than or equal to B if C is non-negative. And if A is larger than or equal to B, then A plus C is larger than B if C is positive. Does everyone understand? I'll take silence as a yes. So now I will I will go through number domains. Olympiad algebra usually focuses on the real domain and sometimes rational and real algebraic, but it rarely focuses on the integers and natural numbers. So natural numbers are integers that are 0 or larger than or equal to 0. So it can be 0, 1, 2, 3, 49, 25. Integers are just whole numbers in general, so it can be negative as well. Rational numbers can be expressed as the quotient between two integers. So it can be 1/2, negative 2/3. And real algebraic can be expressed in algebraic terms of the rational numbers. So it can include square roots, cube roots, and stuff. And then real just encompasses all of them and the transcendental numbers. Don't need to know that well yet. So here's more notation. We say a variable is within a domain by using the membership symbol, which is this funny sign that looks like an E. And then if X was a real number, we would write X is a member of the real numbers. So here the real numbers, the symbol is below with the fancy R. Or X is a member of the domain of real numbers. Okay, so now here are some examples How would you write 3 as a real number? Can someone type it into chat? You would write 3 and then the symbol. And then within the real numbers, right? Yeah, that's correct. And then what does 45 and then membership symbol was the integer domain mean? Means 45 is a member of the integer domain, or 45 is an integer. And lastly, what does A, B, and C within R mean? It means that A, B, and C are real numbers. Okay, so now I will introduce the trivial inequality. It states that for all real numbers x, x squared is larger than or equal to 0. I will give you guys 1 minute to try to improve this by yourselves. Okay, by now hopefully everyone has had like a try at this and should know how to do it. If you haven't, that's not a problem. Oh, okay. So now I'll go through the proof of it. Trivial inequality. For all real x, we have x squared larger than or equal to 0. Okay, so guys, I'm stuck. Can anyone help me? I don't know how to start with this. How do I approach this problem? Can someone type it into chat? And no one's typing it into chat. So, okay, I'll just go through it. So there's 3 cases. If x is positive, if x is 0, and if x is negative. So if we start with the positive case, that's pretty obvious. Positive times positive, it's still positive. And we know that 0 times 0 is 0, right? But if x is negative, we can write x equals negative y, right? where y is positive. So x squared is the same thing as negative y times negative y, which is the same thing as 1 times y squared, right? With this problem. Okay, so now we've covered the trivial inequality. So now we will go through some easy inequality exercises. The first one is to show that for all real a minus b squared must be larger than or equal to 0. So this one, you can literally just plug it into the trivial inequality because you can just write x equals a minus b, right? Since the trivial inequality works for all real x. And then find when ab is larger than or equal to a plus b. I'll give you guys 1 minute to do the second one. Okay, so how would you approach this problem? Inequalities involves algebraic manipulation, right? So, and have you ever seen the expression of ab minus a minus b plus 1? Have you guys ever seen this expression? So this expression factorizes into a minus 1 times b minus 1. And then now we can turn the original inequality to a new inequality of ab minus a minus b plus 1 larger than or equal to 0. So we just need to find when this is true, right? And when is this true? And factorize this side into a minus 1 times b minus 1 then or equal to 0, right? So now we have a few cases. A equals 1 and b equals 1. Then we have that both of them are 0, right? And then if a or b is 1, then we have the both sides are still 0, right? Because 0 times anything is still 0. We can just ignore the one case. If a is larger than 1, then it depends on b, right? Because if b is negative, if b is smaller than 1, then we have positive times negative, right? And what is the sign of positive times negative? The sign of positive times negative is still negative, right? And if b is larger than 1, have that positive times positive, still positive, which is quite obvious. But then we can also have if b is larger than 1, then it's basically the same, but for a. right? Because it's symmetric. And then lastly, we have the case where if a is smaller than 1. Oh yeah, it's symmetric, so we can just ignore the other variable and just focus on one variable. So here I've decided to focus on a. A is smaller than 1. We have that a minus 1 is negative, right? So if we want a negative times something to become positive, it must be another negative, right? So we must b is one must be larger than or equal to b. Because it can also be 0. Still fulfills the condition. Everyone following? I'll take silence as a yes. So we know that if one of the variables is larger than 1, then the other has to also be larger than 1. And if one of the variables is smaller than 1, then the other variable has to be smaller than 1 as well. So now we have two families of solutions. We have a larger than or equal to 1, b larger than or equal to 1, and 1 larger than or equal to a, 1 larger than or equal to b. Okay, and then now we have to show that for all real ai, a1 squared plus a2 squared plus dot 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 an squared is larger than or equal to 0. This looked quite confusing when you first see it, but then if you look at the trivial inequality, then the problem becomes quite trivial. I'll give you guys 20 seconds to think about it. Okay, so now I will go through it. So essentially, what do we have on the left-hand side? We have sum of a bunch of squares, right? So we can pull, these are all in the form of x squared, right? Because a1 squared can be put in the form of x squared, a2 squared can be put in the form of x squared, dot 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 an squared can be put in the form of x. Know that for all real x squared is larger than or equal to 0, right? By the trivial inequality. Now we know that a1 squared is larger than equal to 0, a2 squared is larger than or equal to 0, dot 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 an squared is larger than or equal to 0. And then we can use this property of inequalities that if a is larger than b, or a is larger than or equal to b, then a plus c is larger than or equal to b if c is larger than or equal to 0. Here, a1 squared is larger than or equal to 0, then a2 squared is also larger than or equal to 0. So a1 squared plus a2 squared is larger than or equal to 0, right? And then we can just keep going till an. So this problem looks quite hard, but actually is quite tricky. Now we will cover the AMGM inequality, which is a fundamental inequality of mathematical Olympiad. Most of the inequality problems out there use the AMGM inequality. So this is a quick proof of one of the cases for the AMGM inequality. You know that for all real AB, a minus b squared is larger than or equal to 0, which we showed in this in question 1 of the exercises. Then a squared minus 2ab plus b squared must be larger than or equal to 0, right? Because we just expanded a minus b squared. And then if we add 4ab on both sides, the minus 2ab turns into a plus 2ab, and then the right-hand side turns into a plus 4ab, right? So we just have a plus b squared, which is squared plus 2ab plus b squared, larger than or equal to 4ab. And then if we square root both sides, we have a plus b is larger than or equal to 2 times square root of ab, but we have that we can just rearrange this into a plus b divided by 2 is larger than or equal to. So here on the left-hand side, we have the arithmetic mean, which is the mean, the average you get by adding them together and dividing by the number of elements. And on the other side, we have the geometric mean, which is the mean you get by multiplying them together and dividing by the number and rooting to the number of elements. Where the number of elements here is 2, since we're just using a and b. So when you look at this statement, can you tell if there's any issues with this statement? Like, does this inequality seem right to you for all AB? Or does it seem like it only works for some AB? I'll give you guys 1 minute to try that. Okay, it hasn't been a minute, but we're kind of tight on time. So are there any issues with the statement? Can anyone type into chat? Okay, I'll just tell you guys, the issue with the statement is that we assumed for all real AB, but it turns out this only works for the positive A and B. But if A and B are both negative, we have that square root of AB positive, right? Oh, but we have that A plus B negative. Okay, and then if one of AB is positive and the other is negative, we have that A plus B is uncertain, square root of AB is complex, right? Because it's something times I. And we can't compare real and imaginary and magnitude. Thus, it only works for non-negative A, B, right? Because 0 obviously works. And then when is equality? Well, this inequality is derived from the inequality that A minus B squared is larger than or equal to 0. So this inequality is actually just equivalent. A minus B squared is larger than or equal to 0, right? So now we know that this is the same thing as this one, which tells us that when A minus B squared is equal to 0, we have equality in this one. Can you guys wrap your heads around that? Quite intuitive. And when is A minus B squared equal to 0? How about that right here? We must have x equal to 0 if you want x squared to be equal to 0, right? Means A minus B equals 0, as we decided A minus B to be x, means A equals B, if you rearrange the equation. So the equality condition for A plus B over 2 larger than or equal to square root of AB is when A equals B. So here are some examples. If you want to, so you guys use this inequality that we just proved to do the examples. I'll give you guys 3 minutes and then I'll explain. And now oh wait. Now I will go through the first one, is find the minimum value of A plus B if AB is 1/2. So this problem was made by me, and unfortunately, I think I made a mistake in making this problem. I thought it would be more convenient if I used 1/2, but then I think I intended AB to be 1/4. So we know by the inequality that we just proved that A plus B over 2 is larger than or equal to root of AB, right? Or A plus B larger than or equal to 2 square root of B. It's the same thing as 2 times square root of. But is this actually the minimum of A plus B? Someone tell me by unmuting themselves or typing in the chat. Is it actually the minimum of A plus B? That was a trick question. It is the minimum of a plus b if a and b are both positive and the product. Okay, and then the next question is find the maximum value of AB given a squared plus b squared. So we can just sub in a squared and b squared for a and b, and we know that a squared, b squared is larger than or equal to 2 square root of a squared. It's the same thing as 2ab, right? Everyone understand? And then we can just use that so that a squared plus b squared larger than or equal to 2 times which. So we know that a squared plus b squared over 2 is larger than or equal to ab, right? And if a squared plus b squared is 2, we just have 1 is larger than or equal to ab. So we must have that ab can
啊，
not
怎么看完才开始啊？现在才开始，才过半小时，怎么就看完了？回答
So we know that the maximum value of AB is 1, but how can we get AB to equal 1? Do you guys know how to get the maximum? The maximum must be the equality, right? So when does equality hold? We discussed this earlier. And this, oh, so the equality condition for AMGM is A equals B, right? Which means over here, for 1 to equal AB, we must have A equals B. Equals how much? Equals the square root of 2 divided by 2, right? Which is the same thing. So we must have A equals B equals. Um, oh, let's skip the third one. It's slightly hard. And then let's go to the last one of proving that A squared plus B squared plus C squared is larger than or equal to AB plus BC. I will give you guys 1 minute to think about it, and then I will explain it. Okay, so for this problem, you actually don't need AMGM, this case of AMGM. But if you were to use AMGM, how would you do it? We have three terms, and we have three terms on this side, right? But AMGM turns two terms to be compared to one term, right? So we need to somehow get six terms from the left side and three terms on the right side. How can we do that? Do any of you guys have an idea on how we can do that? I'll give you guys a hint. We can group them into a squared, b squared. And then we can have, similarly, b squared, c squared. Finally, we can have a squared plus c squared. And then what happens if you use AMGM on all of these? If you use AMGM on the first one, you would have is larger than or equal to AB. Am I muted? I'm not. Then the second one gives us larger than or equal to BC. The last one gives us larger than or equal to. Can you guys process that? I'll give you guys around a minute to process that. I need to charge my laptop. Okay, I assume that you have processed this and now understand how to do it with AMGM. Now I'll show you guys how to do it without AMGM. So first, we'll be using the same grouping again. However, if you use the inequality, the trivial inequality, and sub in a minus b for x, we have a minus b larger than or equal to, well, 2ab, right? Larger than or equal to 0. And then we can expand that into a squared, b squared, larger than or equal to. And then if you divide it by 2, we have that it's larger than or equal to ab, right? And then we can just do it, all three of these, and apply this inequality, a squared plus b squared over 2, b squared plus c squared over 2. Thus, the first inequality. That was with AMGM, and this is without AM. So now we will move on to the general form of AMGM. Before we just had the n equals 2 form. Now we have the general, where n can be any positive number, positive whole number. So we have x1 plus x2 plus ... plus xn divided by n is larger than or equal to the nth root of x1, x2 ... So can you guys understand this, or should I explain it to you in Don't be shy. Okay. I'll just explain it to you in easy terms anyway. So it basically tells us the mean from adding a bunch of terms together is always larger than or equal to the arithmetic mean by adding a bunch of terms together and dividing by the number of terms, always equal or larger than the product of these random positive numbers, the root of the product of these random positive numbers. So the proof is quite complex compared to the n equals 2 proof. So we will not go into that in this lesson. And it can be proved by Cauchy induction, which is quite long to explain, and it is on the Art of Problem Solving website. So now we will just go through this one. This doesn't use the general form, but it uses the n equals 2 form. We have a plus b, b plus c, and c plus a larger than or equal to a, b, c. This problem looks so hard, right? But then we know that 8 is the same thing as 2 times 2 times 2. And the problem already has a plus b, b plus c, and c plus d split up. So what would be the natural thought process if you saw this problem? Can someone type it into chat? Well, we had this expression, a squared plus b squared plus, and we had to group it, but here the groupings given to us. So what do we need to do to the groupings? Can someone tell me in chat? Okay, I told myself in chat that you have to apply AMGM to each grouping. Wow. So if we apply AMGM to a plus b, we have a plus b over 2 is larger than or equal to the square root of ab, right? Which is the same thing as this one. a plus b is larger than or equal to 2 square root of ab. Then we can just apply that to b plus c, gives us b plus c is larger than or equal to 2 times square root of bc. And then we can apply it to c plus a, which gives us c plus a is larger than or equal to 2 times square root of b. Are we done now? Yeah, guys, you should chat more. I'm feeling so lonely. Okay, after we do that to each bracket, we are technically done after we multiply them together. So this is the next problem, which also does not use m. And this was in the, I think, Scholarship Calculus 2022 test. So let a be larger than or equal to 0. Prove that a over b plus b over a is larger than or equal to 2. I'll have Guangho Kim present the solution.
Alright. Hold on, give me a second, please.
Wait, go on, I'll just share the Jamboard with you right now.
Alright. Alright.
Oh, wait, Gonko, you don't need to screen share. I'll just share it.
네? 네, 하고 있어요. Alright. So the question that we are given is to prove that A over B plus B over A is greater than or equal to 2. Now, we can directly apply the we can directly apply AMGM onto the statement. Now, by the way we do this is we take A over B plus B over A, and as A and B are greater than 0, these two terms will be greater than 0, which will allow us to apply AMGM. So A over B plus B over A divided by 2 by AMGM is greater than the square root of A over B times B over A, which is square root of 1, which is equal to 1. And now multiplying out each side by 2 gives us that A over B plus B over A is always greater than or equal to 2. Now, yep.
Okay, thank you for presenting that solution.
No worries.
So now going back to this general form, we have x1 plus dot 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 plus xn over n is larger than or equal to the nth root of x1 times dot 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 times xn. So now we will prove the third question of this form. So for non-negative real numbers, a1 dot 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 an, demonstrate that if a1 times all the way to an is equal to 1, then we have that a1 plus dot 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 plus an is larger than or equal to n. Can someone tell me what we should do for this problem? So they want us to prove that the sum is larger than or equal to some number. We are given that the product is equal to 1. So this looks like direct application of AMGM, right? On the left-hand side, we have the sum divided by n, and on the right-hand side, we just have the nth root of the products. And here we are given the product, right? And the product is 1, which is the nth root of 1. And then on the other side, we have a1 plus dot 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 plus an divided by n, which is always larger than or equal to 1, which means a1 plus dot 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 plus an must be always larger or equal to n, right? By multiplying n on both sides. So now this problem is slightly harder than the ones that we've shown you before, but using the same principles, be able to do it. When x and y were both positive numbers, what is the minimum value of 2x plus 3y times 8 over x plus 3 over y? So what would be the first step to do this? Again, they give us two brackets, which signals two groups, right? And then the minimum value might ask us, how would we approach this? Because these two groups don't work if we use AMGM, since these are the products, not the, right? But actually, if you expand this, they still give the sum. Guangho, can you read the solution?
So what we do is we expand out, as Alan has stated, and after expanding, we simplify to get that this product is equal to 6x over y plus 24y over x plus 25. Now, when we perform the AMGM, instead of performing the general AMGM on all three terms, we instead exclude the constant 25 and we apply AMGM on the two terms 6x over y and 24y over x. And by doing so, we get that the two terms added together is greater than 2 times the square root of the product of these two, which is 144, 2 times the square root of 144, which is 2 times 12, which is 24. So we have that the product must always be greater than or equal to 49.
Okay. So this is another form of AMGM called the weighted AMGM. Up until now, we have let the xi's be any real number, and we haven't said that they have to be different, which means they can be the same. So what if we allowed some of the numbers to be same? So what if we say a1 all the way to a5 is equal to 1, a6 is equal to 7, and a7 and 8 are equal to 9. So that still works, because the weighted AMGM relates the weighted and arithmetic and geometric means. So a weight is essentially how much of that number we use in the inequality. So x1 might be used 5 times, which gives it a weight of 5, so w1 would be 5, and x2 might be used 1 time, so w2 might only be 1. This form of AMGM is the most commonly used AMGM, so it's quite important. And then if you extend the AMGM, you can have the QM-AM-GM-HM, which states this monster of an equation, but then we will only show the n equals 2. So I'll give you guys 1 minute to prove that square root of a squared plus b squared over 2 is larger than or equal to a plus b. Guangho, can you present the solution?
One second.
I'll present the solution. So what happens if you square both sides? If you square both sides, why is the font so? you square both sides, you would have a squared, b squared, all over 2, right? Divided by, is larger than or equal to sorry guys, I need to go on to the next. We have a squared plus b squared over 2. This is the new left-hand side. And the new right-hand side is a plus b over 4, sorry. Right? If you expand this, you have 2 times a squared plus 2 times b squared over 4, right? Which is the left-hand side. And then new right-hand side will become a squared, b squared, 2ab divided by 4. But then how can you relate a squared plus b squared and 2ab? Can anyone tell me in chat? So before we show that a squared plus b squared is larger than or equal to 2ab, right? We know by the trivial inequality that a minus b squared is larger than or equal to 0. Right? So the new left-hand side can expand out to become a squared plus b squared, right? And then we can add another a squared and a squared, because it's just 2a squared plus 2b all over 4. Right? And then this a squared plus b squared cancels out with this a squared plus b. Right? Because you can't, they're the same, so you can just cancel them out from the inequality. So we just need to compare a squared plus b squared over 4 and 2ab over 4. But we know that a squared plus b squared is always larger than or equal to 2ab. So by dividing by 4, we have that a squared plus b squared divided by 4 must be larger than or equal to 2ab divided by 4. Right? Which shows us 2m am quadratic mean, arithmetic mean. And then you guys can try the geometric mean and the harmonic mean in your spare time as an exercise. Okay, so this is an application of AMGM. I won't tell you which AMGM, but it might look a bit obvious if you've seen it before. I'll just give you guys a hint. Done by the weighted AMGM. How would you use weighted AMGM on this problem? Okay. Essentially, here we have that A plus B plus C is equal to 3, right? Okay, now I'll get Guangho to explain this. Guangho, can you explain this problem? Or should I do it? Okay, I'll do it. So it tells us that A plus B plus C is equal to 3, right? But then A plus B plus C also has 3 elements, which is A, B, and C. So what would your natural instinct to be after seeing the AMGM? You would turn it into A plus B plus C. Oh yeah, it also gives us 1, which is conveniently A plus B plus C over. The problem is basically begging us to divide by 3. 1, right? So we know that we multiply A plus B plus C to both sides of this equation, that A plus B plus C squared larger than or equal, divided by A plus B plus C, right? 3 times A plus B. It's the same thing as 1. It's the same thing as A plus B plus C over 3. We just multiply by A plus B plus C. And we know that this is larger, oh wait, no. We expand it, we have A squared plus B squared, C squared, 2AB plus 2BC plus 2CA, right? Divided by 3 times A plus. But before, one of the problems was to prove that A squared plus B squared plus C squared is larger than or equal to AB plus BC, right? Do it by grouping. But assuming that we already know that conclusion, we can just say that this new expression larger than or equal to 3 AB plus BC, okay, over 3 AB plus C, right? And then the 3's cancel. And look at this. We have B groups of A, we have C groups of B, and we have A groups of C, right? And over here we have B power of A and C powers of B, and we have A powers of C, right? So this is conveniently the weighted AMGM. By weighted AMGM, we know that this expression larger than or equal to the A plus B, B of A to the B, B to the C. Right, because it's B grouped of A C groups of B, and A groups of. And then now we know that 1 is larger than or equal to this, right? So if we just use this inequality, and we know that 1 is larger than or equal to the A plus B plus C root, A to the power of B times B to the power of C, B to the power of A. If we have X is larger than or equal to, we have X is larger than or equal to Y, larger than or equal to Z, we have that X is larger than or equal to Z, right? So we know that 1 is larger than or equal to the A plus B plus C root of A to the power of B plus times B to the power of C and C to the power of A. And then if we multiply, if we take both sides to the power A plus B plus C, 1 to the power of A plus B to the power of C larger than or equal to A to the B, B to the C, and product of these numbers. We know this is just. Does everyone understand? Basically, from the problem statement, it gave us nothing direct to work with, so we had to make something by ourselves. We have to manipulate it by ourselves. And because it basically begs us to divide A plus B plus C by 3, and keep going from there and then find conclusion. Okay, the next inequality we will go through is the Cauchy-Schwarz inequality, which will be explained by Guanghe.
All right. The Cauchy-Schwarz inequality is essentially a way of differentiating between the product of the sum of squares and the square of the sum of the product. So what the Cauchy-Schwarz statement inequality states is that if you have two sequences, U and V, then the product of the squares of, the product of the sum of the squares of each element, as seen on the right-hand side, will always be greater than or equal to the square of the sum of the product of each element of U and V. And the equality case is interesting, and the equality holds when for each value of I, the ratio between U of I and V of I is equal to every other ratio of U and V. All right. It's very messy to kind of display the Cauchy-Schwarz formula on its own, because it's either sigma notation, which is very confusing, or it's written as a1 squared plus a2 squared dot 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 and everything like that, which is very confusing. So
the Cauchy-Schwarz inequality is derived from vectors. I think there's a Khan Academy video on it if you're interested.
yeah.
So now Guanghe will explain the degenerate case of equals 2 case, make things hopefully more simple.
All right, so what we call the degenerate case here is when there are only two terms, when there are two terms where instead of using U and V, we are using U1 equals A, U2 equals B, V1 equals C, and V2 equals D. And by the Cauchy-Schwarz inequality, we have that A squared plus B squared times C squared plus D squared is always greater than or equal to AC plus BD all squared. And the proof of this is simply by using a very, very neat property. And it's that the factorization of A squared plus B squared and C times C squared times D squared can always be manipulated into the form of AC plus BD squared plus AD minus BC squared. And we know by the trivial inequality that AD minus BC squared always has to be greater than or equal to 0. So what we get that is that AC plus BD squared plus AD minus BC squared is always greater than or equal to AC plus BD squared plus 0, which is just AC plus BD squared, which implies this degenerate case.
So when does equality hold? Here we see that AC plus BD must be positive, right? If A, B, C, and D are all positive. So the only thing that has a hope of being 0 is AD minus BC, right? So we hope for AD equals BC by rearranging AD minus BC equals 0, right? But when is AD equal to BC? It is when A over C is equal to B over D, right? Or it is true when A over B equal to D over D. So that is when equality holds, which is the n equals 2 case of the Cauchy-Schwarz inequality. This identity may look quite messy, but it is pretty useful. It's called the Brahmagupta Fibonacci. You're curious. So now we'll move on to the special case of Cauchy-Schwarz when B1 ... Bn are constant. And this. So if we have A1 plus ... plus An equals 1, we need to prove that A1 squared plus A2 squared plus ... An squared is larger than or equal to 1 over n. I'll give you guys 30 seconds to think about it, and then Guanghe will present. Okay, Guanghe, can you present the solution?
All right. Back to the Jamboard, please. Jamboard. All right. So what we're asked to prove is that given A1 plus A2 plus ... plus An is 1, we wish to prove that the sum of the squares of the numbers is greater than or equal to 1 over n. And the way we do this is by applying Cauchy-Schwarz, where B1 equals B2, and where everything is constant, and Bn equals and it is equal to 1. So what happens is, by Cauchy-Schwarz, the sum of a k squared times the sum of 1, which, since the sum is from 1 to n, this sum will simply be n. And remember, we were asked to prove that the sum of the squares of a1, a2, all the way up to an is greater than or equal to 1 over n, so we can use Cauchy-Schwarz here. And by Cauchy-Schwarz, this will be greater than the square of the sum of a1 times b1 plus a2 times b2 and so on, which remember we have set b1 to be greater than, no, sorry, all b's to be 1. So when we have ak bk, when it's ak times bk, since all the b's are 1, this is simply equal to the sum of all ak's. Now, we are also given that the sum of these numbers of a is equal to 1. So this is purely equal to 1. So what we have derived from here is that n times a1 squared plus a2 squared and on to, sorry, a k squared is greater than or equal to 1. And if we divide by n, we get that the sum of their squares is always greater than or equal to 1 over n.
So this is a quite common application of the Cauchy-Schwarz inequality and is quite important in Olympiad to see. So the next special case of Cauchy-Schwarz is inverses. So the problem statement is let a, b, c, and d be positive reals such that a plus b plus c plus d is 1. And you need to find the minimum value of 1 over a plus 1 over b plus 1 over c plus 1 over d. Okay, hopefully you guys have thought about this problem, and now I will give a brief proof. So first we have a plus b plus c plus d. We know the sum of these variables, and we need to find the minimum value of the sum of the inverses. So the good thing about a and 1 over a and b and 1 over b and c and 1 over c and d and 1 over d is that the product of all of these equals to 1, right? So, and we also need to find the minimum value, so it must be with some type of inequality. So we can turn to Cauchy. Here we know that a plus b plus c plus d 1 over a, 1 over b plus 1 over c, 1 over d larger than or equal to what number? Oh wait, I need to tell you guys what we said the variable. So first, how would we get a, b, c, and d? We set them to be 1 over a1 equals 1 over a, right? Then we can have a2 1 over b, and oh wait, equals a square root of a square root of b, and then dot 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 square root of c and square root of d. And similarly, we can have b1 to be equal to square root of 1 over a, then b2 equals square root of 1 over b, b3 equals square root of 1 over c, and b4 equals square root of 1 over d, but it doesn't have to be in that order. So we would have a squared, which is a1 squared, which is a, we have a2 squared, which is b, we have a3 squared, which is c, and a4 squared, which is d. And we would have b1 squared, which is 1 over a, b2 squared, 1 over b, b3 squared, 1 over c, b whole squared 1 over d. So notice that square root of a times square root of 1 over a is the same thing as square root of a times 1 over a, which is 1. So you can fill in these numbers of the Cauchy-Schwarz. Square root of a times 1 over a plus the other variables. Then all squared. So now we have this side to think about. However, we know that a times 1 over a is 1, right? So it's just square of 4. It's 1 plus 1 plus 1 plus 1. So now we can remove the a plus b plus c plus d because we know that it's equal to 1 by the problem statement. And then 1 over a plus 1 over b plus 1 over c plus 1 over d is larger than or equal to 16. Which tells us that what the minimum value of 1 over a plus 1 over b plus 1 over c plus 1 over d is 16. The next step would be to find when the minimum is, which is necessary for full mark, I think. So we know that the minimum is achieved when you have a1 over a1 over b1 equal to 2 over b2 equal to a3 over b3 and all the way to an over bn, right? But then it's the same thing as b1 over a1. Equivalent to b1 a1 equals b2 over a2 equals dot dot dot, right? Does not really matter, but I'm just going to tell you that it might be used in one of the handle. So here we have a1 divided by b1, a2 divided by b2 equals dot dot dot. So we have a1 squared plus dot 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 b squared equals, oh wait, no, sorry. A squared equals b squared. B squared equals b squared. Means that the absolute value of a equals the absolute value of b equals the absolute value of b. And then a plus b plus c plus d equals 1. And we know that a, b, c, and d are positive, right? Means only one possibility in which a equals b, b equals c equals d, which means equals 1/4, which gives us the minimum value. Okay, it is now 6 p.m., so the class has finished, but if you have any problems or questions, then stay behind and ask them. Thank you for attending this session. The next session will be next week. Oh wait, yeah, next week.